Welcome back. In this chapter, we are going to discuss gases, properties of gases, and some laws that can help us understand gases. We are going to start by just remembering that we have three states of matter. We have our solid, gas, and liquid. In a liquid, the particles move faster because they have more kinetic energy. There is more degrees of freedom. There's a lot of rotation, vibration, translation. In liquids, the particles are more close together, and there is less degrees of freedom. And in a solid, although there is some vibration, there is not that much degrees of freedom because the particles are close to each other and therefore they cannot move as easily. Focusing on gases, gases are going to have lots of energy, therefore they're going to move fast. And the reason for that is because they're going to collide against each other, or they're going to collide with the container that they're in. The way they're going to collide is in straight lines. And when they collide, they're actually going to bounce off, bounce off. They're going to generate energy. So there's a lot of kinetic energy that gases have. So we want to keep that in mind. Now, what happens is gas molecules are always going to be moving and they're going to be colliding. When they strike the glass or the surface that they're in, there is going to be a push. That push is going to be equal to a force. We are going to be able to measure the amount of force exerted by a gas molecule hitting the entire surface. And we're going to do that by figuring out pressure. So pressure is going to be what we are going to be using and to be able to figure out how much pressure these gases are releasing when they strike against another. Pressure is going to be force divided by area, force per unit area. The pressure of a gas results is a result of many many of these molecules colliding. So it's going to build that pressure. The more collision you have, the more pressure you are going to, this is going to result in. So we want to make sure we keep that in mind. The pressure of a gas is going to depend on also the size of the particles, how big they are, the volume of the container, the amount, the concentration of the particles, right? If you have a lot of them versus not having enough. So the higher the concentration of those gases, the greater pressure you're going to have. The reason for that is because you're going to be they're gonna collide with each other. So there's gonna be more collisions as a result, you're gonna have a higher pressure. Also, as volume increases, the concentration of the gas is going to decrease. Let's think about that. You're having a bigger container, but the same amount of molecules. So that concentration is going to change, it's going to decrease because the molecules are the same. What went up is the value. So what this results in is that you're gonna have less collisions because now you have so much space, therefore the pressure is going to be lower. We have an instrument that we use to measure pressure, and this is the instrument that that was the first one. I'm sure we have better methods now, but it's called a barometer. And basically it's a column that is filled with mercury, and that's why one of the units of mercury is millimeters per mercury. As you can see, this is a glass tube, and inside it has mercury, and based on that movement and how much pressure is being lifted there, that's how we measure pressure. Now, the force of the air of the surface of Mercury counterbalances the force of gravity on the column of Mercury. So it's not really that complicated, but we actually use other units nowadays. So we have SI units. If you recall from the beginning of this journey, we discussed SI units, and the SI units for pressure is gonna be Pascal. So 1 Pascal equals 1 Newton divided by meter square. We also have kilopascal. The difference between Pascal and kilopascal is 1,000. You should be able to convert from one to another. We also have ATM, which 1 ATM equals this many kilopascals. 1 ATM equals that many pascals. We also use the most common one, millimeters per mercury. 760 millimeters of mercury is in 1 ATM. We also have inches of mercury, torr, and pounds per square inch. We should be able to manipulate how to go from one unit to the other. We are going to be doing that a lot. You're not gonna directly be asked, but later on you're gonna see how it's going to be necessary for you to know how to convert from one to another. For example, here we're going from ATM to millimeters of mercury. The key is to understand that conversion factor, because are you starting with ATM? In your conversion factor, you want to make sure the ATM goes at the bottom so that cancellation can happen. And since we started with 3 significant figures, when you finish, you should end up in 3 significant figures. So this is a conversion of going from ATM to millimeters per mercury. Another example is how we go from PSI to millimeters per mercury. So there is no direct relationship. So instead, what you're going to do is go from PSI to ATM to millimeters per mercury. So you want to make sure that you refer to that table and be able to have the 2 conversion factors that you're going to need. PSI, your first conversion factor, your PSI must go at the bottom in order to cancel that. Once you cancel your PSI, your second conversion factor, you want to make sure ATM is at the bottom to cancel your ATM. And since you were given 3 significant figures, your answer should be in 3 significant figures when you finish your calculation. Here's a practice problem. Try to do it by yourself before your answer is given. Max, stop that. Here's your answer. Try to do it by yourself first. Here's another question. Here's the answer. Another question. So now that we're familiar with the units of pressure, we are going to be using pressures. But when we're looking at gases, there's more than one characteristic that we're going to be looking. We have what is called simple gas laws. And these gas laws are going to be looking at 2 characteristics at a time. In general, we are going to be looking at 4, but so we're going to be looking at pressure, volume, temperature, and the amount of moles. However, each law is only going to be focusing on 2, which means the other 2 must be constant. For example, we have Charles' law. Charles is looking at temperature and volume. What that means is that pressure and moles must be constant in order for his law to work. So these are called simple gas laws. These properties that we're looking, properties such as pressure, volume, temperature, and the amount of moles are interrelated. When one changes, the other one is also affected. And we're gonna start seeing that. And we're gonna start by going over Boyle's law. And there's a little video that can help you kind of understand. Boyle used what's called a J tube, and he filled this J tube with mercury. And what he realized that they trap air in this J2 and added mercury. And what happened was when he increased the temperature, when he increased the pressure on the gas, he observed a inverse relationship between volume and pressure. What that means that as you increase pressure, your volume what's going down, inverse relationship. So increasing one, so if you increase one, the other one is going to decrease. So if you increase volume, your pressure is going to decrease. So kind of like we were saying that collision, same idea, because now you have less collisions, it's going to decrease your pressure. So the way we actually use that, um, we are going to have it in an equation, and it's gonna look like that. P1 times V1 equals P2 times V2, and the 1 represents the initial, 2 represents the final. So if you look at a graph, notice here that it's an inverse relationship. As one increases, the other one decreases. So that's how, you know, that it relates that as your pressure increases, your volume is going to decrease and vice versa. We can also see in this image how the pressure here is 1 atm and the volume is 1 liter. However, if I increase my pressure, and the way I increase my pressure is by, you know, pushing it down, my volume is going to decrease because the gas molecules collide with the surrounding surface more frequently because you have less volume. So therefore it's gonna build more pressure. So let's do an example on how this will, how something like this will be tested. A cylinder with a movable piston has a volume of 7.25 liters at 4.52 atm. These two are gonna go together. What is the volume at 1 atm? So in this case, they are looking, so at 1.21 atm. So what we're looking here, we're looking for V2. So this is V1, P1, and then this is P2. Notice that both are giving in ATM, so you don't have to worry about it because it's the same unit. So you're gonna be given the equation, which is going to be P1 equals V1, P2 equals V2, and you wanna manipulate this equation and solve for V2. And your answer should be 27.1 liters. Go ahead and try that on your own. Here's your answer. Here's another question that you should try. Notice this is originally. So that's an indication that you're looking for initial volume. Here's your answer. Because the volume of a gas varies with pressure and temperature, chemists have agreed on a set of conditions, which we call them standard conditions. And these standard conditions are going to be used so we can report and being able to compare. And we're gonna abbreviate it by saying STP. When we're saying standard condition, you should automatically know that we're referring as the pressure being 1 atm and the temperature being 273 Kelvin or 0 Celsius. So every time you say STP, you automatically should know that pressure means 1 atm and and temperature means 273 Kelvin. But remember that there's other units of pressure, not just 1 atm. So what that means is that if I'm saying 1 atm. I'm also saying 760 millimeters per mercury. I'm also saying 14.7 psi and so on. So this slide is very important that you know it because all of this means 1 atm and that's STP. Here's another question that you should try to do by yourself, still Boyle's law. Here's the answer that goes along with that. Notice here that it said standard pressure because we knew that. We knew that we were talking about 1 atm. The reason why we kept it as kilopascal because the answer was saying kilopascal. So you could have done this problem using atm and then convert it to kilopascal, or you just remember that 1.01.325 kilopascal is your standard pressure. We have another scientist and he looked at two different properties. And this is the one that you actually do in lab. His name is Jacques Charles. He's French, huh? He looked at volume and he looked at temperature. And what he realized is that those two properties were directly proportional. They were directly proportional when your other two properties, moles and pressure, are constant. One thing that I want to point out about this law is that your temperature must be in Kelvin. You always needs to do your calculations in Kelvins. And I'm sure you guys know how to convert that. Here's the equation. Notice that it's different from Boyle's law. Boyle's law was P1 B1 equals P2 B2 because this symbolizes inversely proportional. Charles' law is directly proportional. And we can see it by looking at this graph where we can see that as temperature increases, volume also increases. If you are questioning what this absolute zero mean, that means the coldest temperature, and the coldest temperature is negative 273.15. The reason why we can't have anything colder than that, because we start getting negative volume. If we extrapolate, we start getting negative volume, and that's not possible. The coldest temperature that you can get is 0 Kelvin, or negative 273.15 Celsius. As you can see here, if we look at the molecular view, as you decrease the temperature, the volume comes down. But in boiling water, you increase in the temperature, you are going to see your volume go up. So you change it from the ice water to the boiling water, the volume is going to expand. So the molecules are going to move faster because of the increase of temperature. When the temperature of a gas sample increases, the gas particles move faster. Think of it as they getting a shot of energy. When you get a shot of energy, you move faster. They're going to collide more against each other or against whatever container you have in. The force exerted in each collision will be greater. The only way for pressure to remain constant is for the gas to occupy a larger volume. So the collision becomes more frequent and occur over a large area. How will we ask you for this type of question? Notice that it says a gas has a volume of 2.57 liters at 0 Celsius. The first thing I will realize this is I will convert the Celsius to Kelvin. What is the temperature at 2.80 liters? So it looks like I'm asking for my initial temperature. So you want to set up your equation, which is V1. And the way I usually solve that is I crisscross. Some people like don't know how to solve it. So the way I do is V1 T2 equals V2 T1. And then it's easier since in this case we're solving for T1, divide both sides by V2, and is T1 equals V1 T2 V2. That's just a trick. Crisscrossing kind of helps. Let me know if you want me to re-show you. But once you have, and that's the key though, being able to manipulate this equation. If you don't know how to manipulate it, you're going to get it wrong. So the first thing will be, first step in the process of solving your equation is to convert those Celsius to Kelvin. And then once you have that done, input it in your equation and you would arrive with your final answer. And since the question was given to you in Celsius, you should also report your answer in Celsius, even though when you are solving the question, you should solve it in Kelvin. So it's a little bit more work. Here's another question. And the answer for this would be, it would be 729 milliliters. So make sure you get that when you try to solve it yourself. And we can also do it together. A sample oxygen has a volume of 420 milliliters and temperature, convert that to Kelvin. And they want it in Celsius. So at the end, don't forget to convert it to Celsius again. And in this case, your answer will be 170 Celsius. Here's another question. Here's the answer. We are going to be looking at another scientist, and this scientist is gonna be Emilio Avogadro. So he's another scientist that he looked at volume and the number of modes. And he also realized that they are directly related. They are uh, directly related. As one increases, the other one also is going to increase. For his law to work, we wanna make sure we assume that you're going to have your temperature and your pressure are going to be constant. So what his law is saying that the sample increases with the volume increase. So they are directly proportional. As you can see here, you increase in the number of moles and your volume is also increasing. Here's how we write the equation. B1 divided by N1, B2 divided by N2. As you can see here, there is a kid that is putting air into the balloon, which that means that he is increasing the number of molecules in their gas molecules. As a result, the volume is increasing. Notice here a question, and be careful with this particular type of questions. A 0.225 mole sample of helium has a volume of 4.65 liters. How many moles must be added? Now, what is the final moles? How many moles must be added to give you this many liters? So at the beginning, yes, you are gonna solve for N2, but that is your final. But they wanna say how much must be added. So you need to take your final that you saw minus your initial, and that will tell you how many moles will be added. So for example, when you manipulated the equation and you come out with the answer, that's N2, but they're not asking for N2. They are asking for how many moles must be added in addition to what you already started with. If you started with 0, well, yeah, you will add 0.314, but you didn't start it with 0. So what you're gonna do is take your final minus initial, and this is the moles that you must add. Here's another question for you to practice by yourself. And here's your answer. Here's another question. And here's your answer. Okay. Next, we are going to combine all these simple gas laws, your Boyle's law, your Charles law, your Avogadro's law, and we are going to derive them and relate them, and we are going to arrive with the ideal gas law, which is PV equals nRT. Your R is your gas constant, and yes, your R has 4 units: liters times ATM times volume divided by volume times Kelvin. It is very important that you write your units when you are writing your R constant. That will let you know if you have made a mistake. For example, in here, P represents pressure. Because of your R, pressure has to be in ATM. V represents volume. Volume must be in liters. N represents moles, T represents temperature, which must be in Kelvin because of the R that you're going to be using. So R is called your gas constant. So when I'm from here, you're gonna be looking either for pressure or you're gonna be looking for volume or temperature or moles, which means the other 3 units must cancel. So they have to be the same unit in order to cancel it. So here kind of gives you there's other law, we didn't mention the Gay-Lussac, but that law also, it's a law that help arrive to the ideal gas law. So we're gonna stop here. When we come back, we're gonna do some practice problems on the ideal gas law. Okay, so keeping this equation in mind, we are going to do some practice problems of the ideal gas law. Start with how many moles, which means they're asking you for N, are in a basketball with a total pressure of PSI. This should tell you that we need to convert it to ATM. You have volume and Celsius, which you need to convert to kelvins. In this case, we are looking for N. So remember, PV equals nRT. You want to manipulate the equation to solve for N. Here it is. Divide both sides by RT, and you arrive to that equation. PSI, this is your conversion factor to ATM. Then convert your Celsius to your Kelvin. And now you're ready to plug it in the formula. Notice that here's your constant. So your ATM cancels, your Kelvin cancels with your Kelvin, your liter cancels with the liter. The only unit that did not cancel is your moles, which is what you wanted. And that gives you your final answer. Here's another question where there's asking you calculate the volume. So you're looking for volume, PV equals nRT. So you solve for volume, nRT divided by volume. They're giving you the moles and they're giving you the ATM, so you don't have to do any conversion there. Notice once again, you put all the units in your R, so you should be able to cancel everything except for your liters, which is what you wanted. Here's a question for you to practice. Notice that it's got said calculate the volume. So they are giving you pressure, which you need to convert in ATM. They are giving you temperature. R is a constant, but they're giving you grams. So, but you need moles in the equation. So you need to convert this to moles. That's the first thing you need to do. Then you need to convert your Celsius to ATM and your millimeters of mercury to, your Celsius to Kelvin and your millimeters of mercury to ATM. First step is convert your grams to your moles, which we already know how to do that by using the molar mass. So this is your N. Then your P, millimeters of mercury to ATM. Then your Celsius to Kelvin, this is your T. And then you plug it in your equation to get your volume. So sometimes you have to prepare everything to plug it into the equation. Here's another practice problem. Notice that it says STP. Well, we already know that we have 1 mole. So remember that I told you pressure equals 1 ATM. And they're asking you for the volume. Temperature is 273 kelvins. The STP volume is 22.41. ATMs cancel, Kelvins cancel, moles cancel, except for liters. Determine the volume if you are given moles, Celsius, and ATM. Once again, PV and RT. You want to solve for volume, so that means volume, divide both sides by P. And plug it in your equation. One more question, and this is actually an important question, and I want to make sure that you guys know how to do it. So notice that it says you have your liters, so you have your your volume, which is 2.3 liters. You have your P, which is 1.2 ATM. You have your T, which is 25 degrees Celsius plus 273. Then that's going to be 298. Now you have your R, 21. Now we are solving for mass. So basically N. So N is equals PV divided by RT. So that's going to give us N equals P, which is 1.2 ATM, V, which is 2.3 liters, R, which is 0.0821, times temperature, which is 298 K. My units cancel, ATM, and my moles should not cancel. So that gives me 0.11 moles. But they want to know how many grams. So you need to convert 1.1 moles times 1 mole, 1 mole. How many grams? One thing that you want to remember here is nitrogen. Nitrogen is a diatomic. So it's not 14, it's 28 grams. That should give you 3.1 grams. Make sure you remember that because a lot of people will put 14 there and that will be wrong. Now we're going to switch gears and we're going to talk about molar volume, which we already discussed. We calculated to be 22.4 volume. What that means is that 1 mole of any gas at STP will occupy the volume of 22.4 liters. For example, if you have 1 mole of helium, you're going to have 22.4 liters. If you have 1 mole of xenon, you're at STP, the case at STP, you're going to have 22.4 liters and so on. So we can use this to do calculations. Notice here that the gas, as long as it's at STP, ST, you're going to have the same volume. For example, and I like this question, how many liters of oxygen at STP can be made from decomposing 10 grams of lead to oxide? So they're giving you the equation. So notice how we are going from 10 grams of lead oxide, and they want to know how many liters of oxygen. So we need a relationship. So always, every time I'm giving you grams, you always want to convert it to moles. So 10 grams, oh, it's 100, not 10. 100 grams of this gas, and the molar mass of this will be 230, oh, I have it here. Notice here how grams to moles, so your grams cancel. They always do a mole to mole relationship from the balance equation. So now it's, you want to make a relationship between this gas and oxygen because this is what you want to end up with. So in this case, these two are, everything else can be ignored. Then because it's at STP, that means that 1 mole of that gas equals that much, how many liters? That leads you to your final answer. Now we can use this, and we can um, use the ideal gas law to figure out the density at standard conditions. Density is a ratio between mass and volume. So usually density is generally given in grams per liter. Well, we can know if we know the molar mass. At STP, we know the volume. We can figure out the density of a gas. For example, notice here we have helium has a molar mass of 4 grams per mole. And since 1 mole of it is 22.4 liters, cancel moles. The units that do not cancel is grams over liter, which is a unit of density. This is the density of the gas. And we can do the same to figure out the density of nitrogen. So in generally, if we have 1 mole of any gas at STP, we can figure it out the density of that gas. However, what if we don't, is not 1 mole and it's not at STP? We can use the ideal gas law to figure it out the density of a gas, because we can derive this formula, manipulate it, and arrive with this, where M stands for the molar mass of the specific gas, and then P for pressure, R is your gas constant, and your T for temperature. Density is directly proportional to the molar mass. What does that mean? As the molar mass goes up, the density will also go up. Okay? Calculate the density at N2. It does not say STP, which means we need to use the other equation. We gotta convert this to Kelvin. We gotta convert this to ATM. So you're gonna go back to the equation that I gave you, where this is the molar mass, this is the temperature, this is the constant, and this is the pressure. You are giving everything. So in this case, it says N2. So that means that we are going to do 28 as the molar mass. This is just converting your millimeters of mercury to ATM, your temperature to Kelvin. And notice here, we plug everything is ATM, ATM cancel, your Kelvin, Kelvin cancel, your mole cancel. The only 2 units that did not cancel are your grams per liter, which is a unit of density. So the density of nitrogen under these conditions is 0.852. Try to solve this one by yourself. The answer will be 1.84 grams per liter. And we can do it together if you guys don't arrive to the answer. Here's another question. We're still calculating the density of a gas. We're gonna convert this to ATM. Notice that it's in here, is telling you that it weighs. So they're giving you grams. So remember, density is grams over liters. You already have grams. What does that mean? That you need to use PVNRT to figure out volume. So because you don't know which gas, so you can't use the molar mass. So use PVNRT first. PV equals NRT to solve for volume. Once you have your volume, you're going to take 9.988 grams and divide it by the volume that you found, and that will give you your density. So try it before I give you the answer. Here's the answer. Good. We can also use the ideal gas law to figure out molar mass. Because if we are giving grams, we can calculate moles, and you know the molar mass is grams over moles. So we can actually use PVNRT to arrive to the molar mass of a, you know, a potentially gas. We won't know, but it helps us identify a gas. For example, in this question, calculate the molar mass of a gas. So you don't know which gas. Given, here's your grams, so you're not gonna need this number until the end, but you are given volume, temperature, and pressure in R, which is constant. Calculate the molar mass is grams over moles. What you need to do, similar to what you did before, use PVNRT, but in this case, solve for N, which is your moles. Once you have done that, so here's, calculating the conversion. So notice here, you calculating your moles. Now, how do you get molar mass? Grams. So you're gonna do the 0.311 divided by your moles, and now this is the molar mass. So now you can figure it out which gas it is, which potentially can be oxygen, because oxygen is a diatomic, so 16 times 2 is probably that. But it's not certain, but you can guess which gas it is. Here's a question that you can try by yourself, and I'll give you the answer. The answer is 126 grams over mole. Here's another question, same idea, but in this case, you're going to notice that they're giving you the grams. So use PVNRT to solve for moles first, but always make sure you convert this to ATM, this to Kelvin, and you already have liters, so you don't have to worry about that. Here's the solution. The next item that we need to talk about is going to be focusing on pressures and how we're going to be looking at a mixture of gas. And each gas is going to exert a pressure, which we call partial pressure. But when you mix the gas, the total pressure is literally going to be adding those individual partial pressures. For example, air is composed of nitrogen, oxygen, argon, and carbon dioxide. Each of them exert a pressure. So we do by percentage will be 78%, 21.9, and 0.04. If I wanted to know the total pressure, all I need to do is add those numbers. So simple as that. Those are called adding the partial pressure. So the partial pressure is the pressure that is exerted by any individual gas. We can calculate the partial pressure by two different methods. If we know the total pressure, we can calculate the partial pressure, or if you don't know the total pressure, but we know the number of moles of that container, volume, and temperature, we can calculate the partial pressure. So two different ways of calculating the partial pressure. So if you know the total, so it will be P total equals PA plus PV. This is just like partial. You can figure it out A if you know this and you know this. If not, we're gonna use another equation, the PV-nRT, to solve for the partial pressures. And those two formulas are coming up. So this whole idea, it's going to be under Dalton's law of partial pressure, where he says that the sum of the partial pressure of all the gases in a mixture is equals the total pressure. Notice here, these are the two. So if you know the total and you know that all the partial pressures, you can calculate the partial pressure of A. However, if you don't know the total, you can calculate the partial pressure by just using the PV-nRT. So here's an example where you actually know a mixture of helium, neon, and argon. So it's 3 gases and the total pressure. So you know the total, you know the partial pressure of helium, and you know the partial pressure of neon. As a result, all you need to do in order to find the partial pressure of argon is to take the total pressure, subtract the partial pressure of neon and the partial pressure of helium, and that should give you the partial pressure of argon. So this is the easy way of doing it. There's another type of problem. Determine the mass of argon in a mixture. So this is given to you. They're giving you, oh my God, sorry about that. They're giving you the partial pressure of helium, neon, and the total partial pressure. So what you can do, you're looking for the mass of argon, but they're not giving you information about argon. So the first thing you need to know is figure out the partial pressure of argon based on that information that is given. So you're gonna take the partial, once you find the partial pressure of argon, you can put it on your PV-nRT to solve for moles, and then for moles, you can go to grams because that's what they're looking. That's exactly what they did here. This is the partial pressure of argon. This is the total pressure minus the pressure of helium and neon. So that's the partial pressure of argon. We use PV-nRT, this converting it. PV-nRT, now they give us the moles of argon. Then you can go and find the grams of argon. So try doing this one by yourself. Here's the answer. This is a really good problem. I like this problem. Now we're moving to mole fraction. So mole fraction is, it's another technique that we use. Mole fraction is pretty much the fraction of the total pressure that a single gas contributes equals to the fraction of the total number of moles. So this is another way of using partial pressure, of determining partial pressure. If you know the mole fraction and you know the total pressure, we can calculate the partial pressure. The partial pressure is going to be basically part over whole. Let's give you an example. For example, here, if you are asking nitrogen has a 78 composition and you need to know the partial pressure, well, in this case, you know the total and you know that that's the total ATM, and this will be the mole fraction. So this will give you the partial pressure of nitrogen. But let's do a more interesting problem where it says that we need to find the mole fraction and the partial pressure. So we need both, right? In a 12.5 liter tank with 24.2 grams of helium and that much grams of oxygen. So how do we attack this problem? So notice that they're giving you that you need both. So you need the partial pressure of helium, the mole fraction of helium, the partial pressure of oxygen, and the mole fraction of oxygen. The first thing you need to do is figure out the total pressure, right? So you need to figure it out first. In order to do that, you need to find the partial pressures. So how are you gonna do that? Well, you need to first find the mole fraction of each. For example, first we take the grams of helium and convert it to moles. Then we take the grams of oxygen and convert it to moles. Now, how do we find the mole fraction of helium? We are going to take this divided by the total, which is the addition of those two. This is the mole fraction of helium. So we have one out of the four things that they want me. We're going to do the same thing for oxygen, except the number at the top is going to change because what we want is the mole fraction of oxygen. The bottom is the same because it's the total. This is the total. So now we have the mole fraction of oxygen. Next step is erasing this, is to find the total pressure. The total pressure, and the way we're gonna do this is by doing the PVNRT. This N must be the total moles. So the addition of the two moles, and now we have the total pressure. Now we can find the partial pressure of each. How? We have the mole fraction of helium times the total pressure, and that gives you the partial pressure of helium, and we apply the same thing for oxygen. This is another example where basically you are giving percentages, which is your mole fraction, and then you are giving the total pressure. So you can calculate the partial pressure. This one is more easy. And you can do it. Practice on this one, pause it and try to do it by yourself. Here's the answer. I have one more question that I would like to try, like you to try. Pause it before you look at the answer. Okay. Now, all of this, we can use it to make relationships, just like we did stoichiometry. We can do some relationships in reactions involving this type of gases because we can relate volume, we can relate moles. So we can use stoichiometry calculations involving gases if we use the ideal gas law correctly. So sometimes they are going to give us volume or temperature or A of a gas A. We can convert it to moles, then do a mole to mole relationship using the balance equation, and we can end up with information about gas B. Just as a reminder, STP conditions, and let's do a problem. Calculate the numbers of carbon dioxide. So they're carbon dioxide, which is here, that forms an STP that they're giving me information of calcium carbonate. So notice that they're giving me moles of calcium carbonate. So we did this similar already. Convert it to moles, and then, oh, well, they already gave you moles. So moles, then this do a mole to mole relationship using the balance equation. And then as STP, 1 mole of gas equals 22.4 liters of carbon dioxide. And notice how you end up with liters of carbon dioxide, which is what you want. So you made a relationship between your reactants and your products, which is stoichiometry. Now here's another question. How many moles of ammonia, so here's they're asking you about ammonia, are formed by a complete reaction of hydrogen, but notice that they're not even giving you grams or moles. They're giving you liters of hydrogens, the temperature, and the ATM. So the first thing you need to do is use the information they're giving you about hydrogen to figure it out the moles. So use PVNRT first. So it's reverse. First, you use PVNRT. That gives you the moles of hydrogens. Then you can do a mole to mole ratio to figure out the moles of ammonia. So in this one is reverse. You use PVNRT first before doing the mole to mole ratio. Sometimes it's the opposite. What volume of hydrogen, okay, is needed to make, notice what they're doing here. They're giving me information about methanol, but they're giving me grams. So what I will do here is convert those grams to moles. Once I have the moles of methanol, I will convert it to moles of H2 by a mole to mole ratio. Now I have moles of H2. Since they need the volume, after that, I can just stick it in the PVNRT equation and get me the volumes that I'm looking. So it's, you have to read it and you have to see what way to approach it. There is not one key. I can't tell you every time you see this problem, you're gonna use this equation. No, sometimes you use a PVNRT first. Sometimes you have to do a mole to mole ratio first. Sometimes you have to convert to grams, to moles first. So it just depends. You have to read the question. Try this on your own. Here's the answer. One more. Here's the answer. I'm more than happy to do some of these problems together because they are very important. You have to read the question and figure out how to attack the problem. So this is just a review on property of gases, how they expand, how they have low density, how they are compressible, how they have a lot of kinetic energy, which brings us to the kinetic molecular theory, which is pretty much a theory that just gives the characteristics of all the gases. So it's important that you become familiar with this. The kinetic molecular theory says the particles of a gas are constantly moving. The attraction between particles is basically, you can ignore, is negligible. When the moving gas particles hit another gas particle or the container, they do not stick, but instead they will bounce off and continue moving in another direction. Also, part of the molecular kinetic theory says that there is a lot of empty space between the gas particles. This is everything I already said. This is just a summary and put together in the kinetic molecular theory. The average kinetic energy of a gas particle is directly proportional to the Kelvin temperature. So if the temperature increases, the average kinetic energy will also increase. So as you raise the temperature, the molecules are going to speed up. And because the gas particles are constantly moving, they strike the sides of the container with force, resulting in pressure. As you can see here, we can see that the pressure it's constantly doing. When you compress the container, you're going to increase the pressure because you're squeezing. That means there will be more collision between each other. There's two terms, some terms that you are going to need to become familiar with in order to, for multiple choice. Molecules in a gas travel in a straight line until they collide with one another or the container. We already knew that. The average distance a molecule travels between collision is called the mean path, mean free path. So you want to memorize that. Mean free path decreases as pressure increases, and that makes sense because that means you have less way of moving. Two terms, diffusion and effusion. Diffusion is when the molecules, and these two terms are on the exam, I'm warning you. Molecules are spreading out from a high concentration to a low concentration. Effusion is when molecules escape through a small hole into a vacuum. That's called effusion. The rate of diffusion and effusion of a gas are both related in its average velocity. For gases, the same temperature, this means that the rate of the gas movement is inversely proportional to the square root of its molar mass. So that's a little bit more detail than I need you to know, but that's just in general, kind of know the two definitions and understanding. They give you here's a picture of effusion. Now, real gases is pretty much just kind of reading, become familiar. It's just pretty much telling you that everything that we have been talking about has been ideal gas law. Basically, we have these certain conditions, right? Real gases often do not behave like ideal gas law. They might be some attraction between them. So that's a whole different chapter that we can discuss at some point, but I just want you to know that there is a difference between real gases and ideal gases. Everything that we have studied in this chapter is ideal gases. As you can see, this is the ideal gases. This is how they behave. This is the unideal gases. So for the rest, oh my God, what happened to this? The rest, just read it, and it's just kind of summarizing the chapter. That concludes this chapter, and that concludes the lecture for today.